So first of all, before we kind of talk about like these three scenarios, it's a general thing, is that the positive version of an acid is always more acidic than its neutral version. You see, I didn't say any positive acid is more acidic than any neutral acid. I said the proton version of the same acid is more proton, so is more acidic. Like meaning, like for example, like this is more acidic than this. Of course, this is an example, but yeah, like the pK of this one is 16, this one is minus 2. But this applies for any example. And same thing applies to bases, is that the negative version of a base is always more basic than its neutral version. So like this is more basic than this. So that's regardless of, I mean, I guess you see like REO doesn't apply to this because I mean, we're actually the same pretty much. It's just the charge that is different. Yeah. So, okay, so now actually, so this is what's general, like applies to any acid-based question. Now let's talk about these cases with neutral acids with negative bases. So, and then if you're wondering, can you be neutral acid with the base not being negative? Of course not. It has to be negative. Because when you're neutral and you lose a bond, you become negative. So there's like 4 ways to compare the stability of negative conjugate base. So, so it's yeah. So if you, I guess, I mean, technically Rachel is new this year. So, because I mean, in Chem 133, don't call it REO. So A is for different atom between the two. R is for resonance. I is for induction. And O is for orbital. And also they didn't have orbital. They were calling it they were calling it electronegativity. Different labels, same concept. So let's talk about it. So when it comes to atom, first of all, what do I mean? So that means that the atom that is carrying the acidic hydrogen is different between 2 acids. So if the 2 atoms are on the same, so by the way, before we're gonna start, so just a reminder that the periodic trend for electronegativity is like this, where F is the most electronegative element in the world. So that's En, and radius is exactly the opposite. So you just need to know when to focus on which, because they literally the opposite. But here's the thing. The reason I'm going to tell you what I'm going to tell is that on the same row, electronegativity is the dominant factor, and on the same column is the radius that is dominant factor. So if the two atoms are in the same periodic row, electronegativity is the dominant factor. So the more electronegative the atom, the more stable technically the negative charge on the conjugate base. Stronger acid. So technically it applies to any atoms that are in the same column, same row. But again, we don't talk about all of the atoms in the periodic table. It's mostly, to be honest, just oxygen and nitrogen and carbon. So like this. So for example, like if you're comparing the acidity of OH to NH2, then you're going to compare them. And so you see, this is what I mean. Like that negative charge is much more happy to be on an electronegative oxygen than electronegative nitrogen. So this is more stable base, which makes this guy a stronger acid. Literally. Yeah. And then if the two atoms are on the same column or group, same thing, on the periodic table, the dominant factor is radius, or as they call it in Chem 123, polarizability. But I don't think they call it polarizability in this course. Again, same thing. Who cares what they call it anyways? But I'm just saying. So the dominant factor is radius. The bigger the radius, the stronger, well, technically the more stable the conjugate base, which means stronger acid. Yeah. So for example, so like S, like on a pair, like S, ones that actually come up the most are group 16 ones. So SE is beneath S, and S is beneath O. So like when you're comparing like the OH to SH, and then you compare and say, well, this is O negative versus S negative. So O is still more electronegative than S, but we don't care about that because they're on the same column. So S is bigger, so it's more stable. So this is going to be stronger acid. And same logic, we normally don't compare acids to each other. I mean, besides knowing their pKa table, pKa number. But technically, you can actually compare HI and HBr and HCl to each other. How come? Because their conjugate bases are all on the same column. So this. Yeah. So pretty much like when you're comparing these guys and the atoms are different, it's either different atoms in terms of the same column or same row. And you're like, what if it's neither? It's never not going to be like that. So fun. Cool. Any questions? Okay. So the next one is, look, resonance. But the thing is that resonance, it's actually the same as what I said last time in Q 133. There is layers to it. It's not like yes or no. So most people, they're like, remember, like you're trying to find a difference between them. You'll see what I mean. So look, resonance, and this, which is very true, that it actually, that's how it relates to the entire course, is that, look,